Hi there, welcome to week 2. In this week and also in the next one, we will deal with the estimation of the PD, the probability of default of a counterparty. We will see different approaches and today in this class we introduce the most important theoretical model for the estimation of the PD, that is to say, Merton's model. We will see that Merton's model relies on some strong assumptions that makes the model not really useful in practice, but nevertheless, Merton's model is still a very important benchmark in the class of credit risk models, and for sure it is the starting point of a series of very important models that you can find in the literature and that are also used in the industry. Models like Moody's KNV and JP Morgan's credit matrix. So it's very important to understand the functioning, the mechanisms behind Merton's model, because that will help us in understanding all the other models. Merton's models was introduced in 1974 by Merton, who is a Nobel Prize winner for economics. And Merton's model is to credit risk modeling what Black-Scholes is for pricing. In fact, we will see that even if these two approaches obviously start from different starting point, one is pricing, one is credit risk, essentially they converge to a very similar solution. And that's why in financial mathematics we typically speak of Black-Scholes, Merton's formula, and not just Black-Scholes or Merton, because they really share something worth investigating. Merton's model is the prototype of the class of models that go under the name of structural models of default. In this class, we typically see a stochastic process that mimics one of the quantities that can describe the financial solidity of our company, for example, total assets or the equity ratio, and we look at the probability that this quantity essentially touches or overcomes a given threshold. In Merton's model, the process that we consider is essentially a process mimicking the total assets of the company, and the threshold is defined by some sort of liability. Let's start by considering the economy in which we perform our evaluations. As usual in financial mathematics, we make some simplifying assumptions to make our computations easier. First, we assume that the two fundamental theorems of asset pricing hold. This means that there is no arbitrage on the market, that is to say, there exists at least one risk-neutral measure equivalent to the physical one, to the market one, if you prefer. Moreover, and this is the second theorem, the risk-neutral measure is actually unique and markets are complete, so that all financial products and risks can be assessed and evaluated. These are rather technical requirements for stochastic calculus purposes. More details on the course platform if you wish. We then assume markets to be frictionless, meaning that there is no transaction nor hidden cost. Finally, we assume the Modigliani-Miller theorem on the irrelevance of the financial structure. In other words, the value of a company is independent from the financing sources. A company totally financed by debt is as valuable as another one totally financed by equity, provided that their total value is the same. If we move to the company level, in Merton's model we just deal with limited companies. The reason will be clear quite soon. In practice, we want shareholders to abandon the company in case of a default. The company can finance itself with equities, that is, issuing shares, or by debt. Debt is represented by one single debt obligation or zero coupon bond with face value capital B and maturity capital T. As we will see, this is a strong assumption and one of the points of weakness of Merton's model. Moody's K&V, for example, tries to solve this problem. If ST denotes the value of equity at time t and BT represents debt, we have that the value of the company at time t, VT, is equal to ST plus BT. We then assume that the company cannot pay dividends or issue new debt before capital T. This is meant to make computations easier once again. Regarding default, we define it as the situation in which the company is not able to pay debt holders by missing the repayment on debt at time capital T and only at time capital T. So, given all the assumptions together, we have that our counterparty, our company, can only default at time capital T, not before, not after. That means that at time capital T, we will essentially evaluate the event default for the counterparty. You can understand that this is clearly a point of weakness of Merton's model, because we know that even if we fix a time horizon, so our capital T, then default in reality may happen at any time before, not just at maturity. Given all the assumptions we have, at time capital T, we have two possible scenarios. If the value of the company's assets exceeds the liabilities, that is, V capital T is larger than capital B, everyone is happy. The debt holders receive capital B, while the shareholders receive the residual value, that is, V capital T minus capital B. Conversely, if V capital T is smaller than or equal to capital B, we have a default, as the company is not able to meet its obligations. Thanks to the limited company assumption, shareholders do not have any interest in providing new capital, since it would go directly to debt holders. Instead, they hand over control of the firm to debt holders by exercising the limited liability option. Debt holders thus liquidate the company and distribute the revenues among them. Debt holders get V capital T and shareholders get 0. Notice that we assume that the company defaults also when V capital T is equal to capital B, because we do not want a company without any equity. However, from a probabilistic point of view, this is irrelevant, given that we will play with continuous distributions. Now, have a look at the equations here. They should be familiar to you. If you have a look at the equations, you see that S capital T, that is to say, the value of equity at maturity, capital T, corresponds to the payoff of a European call option on V capital T, the total value of the company, with exercise price capital B, the liability level. And for what concerns the value of debt at maturity, this corresponds to the liability level capital B minus the payoff of a European put on V capital T, again with exercise price capital B. So you see here the connection between Merton's model and Black-Scholes. In the next video lesson and on the course platform, we will give more details. But it is already clear that Merton's model is only a stylized description of a default. In reality, default can occur at many different times and not only at maturity, and not all companies are limited companies. Nevertheless, despite its simplicity, Merton's model is also able to give an effective view of the potential conflict of interest between shareholders and debt holders. The first have an interest in the company investing in risky projects that increase the volatility of the underlying security, the value of the company, while the second prefer a less volatile and risky asset value. Relying on market quantities like equity and debt as an input in order to derive the probability of default, Merton's model is considered a capital market model. For the moment, that's all. Thanks for your attention. Goodbye.